Welcome everybody to the Study Club. This week we have Bobbin Threadbare who's going to share with us AirScript. And I believe there's the paper by the StarkWare guys that you had as like as something to read in advance. And there's also, as far as I could see, like some sort of repo. What did you share? It was like a GitHub.
Yeah. So basically what I would like to do, and maybe let me see if I can just go to the agenda slide. So the first two parts here is basically just a slide with some information, presentation, and so forth. But the second two items is I'd like to do actual examples, and the repo contains those examples. So if anybody wants to clone it and kind of follow along, I will actually be sharing my screen and how I write AirScript and how generate execution traces and so forth. So if anybody's interested, you're more than welcome to do it. But if not, or if you're not able to, I'll be doing the same thing on the screen. So either way works.
Very cool. All right.
All right. So basically, the first thing I would like to do is to just go through some kind of concept behind Air and what exactly is arithmetization and so forth, and then very quickly go through Stark basics and then jump into some examples. And feel free to interrupt at any point, ask questions. If you think I'm misstating something, let me know. I'll be going fairly quickly because I think a lot of this is familiar to many people on the call. But if something doesn't sound it's confusing or anything, just speak up. Okay. So just to set the context, if you think about computations in general, we can think about them in two different ways. There is the circuit, or there are two different ways to represent them. There are circuit computations or machine kind of representation of a computation. And the first one is done with arithmetic circuits. You can reduce a computation to a kind of a circuit. And the second one is, could be represented as a transition function that explains how a state of computation changes from one step to another. And in terms of arithmetization, for the circuit computations, we have R1CS, and this is what is typically used. And for machine computations, we use Air or algebraic intermediate representation. And kind of high-level benefits, and again, there are a lot of nuances here, but kind of high-level benefits, R1CS is fairly easy to kind of reduce, get from a general purpose computations. It's the composition is fairly simple. It's not necessarily the case with Air. It's not as easy to kind of compose different kind of computations together. But at the same time, Air, because of the way it is represented succinctly, kind of allows you to have potentially faster proof and verification times as well. And in terms of languages, and sorry, you see like my dog in the background, I'll try to block him. But in terms of languages, there's a bunch of languages for R1CS, Narki, Circum, Socrates. And for machine computations, as far as I know, as of right now, there is AirScript and AirAssembly. And I'll be focusing on AirScript for this kind of session, but AirAssembly is a kind of lower-level language that AirScript compiles to. And in terms of where different types of representations are used in, so most snarks, as far as I know, maybe even all snarks are relying on R1CS constraints or R1CS representation. And Air is, as far as I know, again, is only used in Starks. I don't know of other systems that use Air representation, but I might know everything. Okay, so any questions about this part? All right. So let's
say that. Sorry to interrupt. Would it be fair to say that AIRS could potentially be used with a pairing-based system and a SNOC to generate a SNOC?
It could be, but to be honest, I'm not sure how that would be done. But I mean, it's possible, I guess.
Yeah, you should be able to use the compiler in Marlin. Like, I think you can convert the Air RSIOP into an AHP, and then use the penultimate scheme, KZG or DARKS.
Okay. So then I guess you can, in theory, use Air with other systems as well.
Yeah, just no one's done it.
Yep, makes sense. Okay, so kind of to understand Air, there is kind of, few high-level concepts that once you kind of understand what they do, I think everything else is fairly easy. And the first kind of base concept is a computation state. So a state can be represented as one or more registers. And these registers are field elements in some field that you've chosen for the Stark. And again, it could be either one or more. If you want to do anything useful, it's probably more than one. And it's kind of a snapshot of a computation at a given point in time. And you can think about it as almost as a computer processor. It has registers, and this is similar to that. Those registers have states at a given point in time. So the next kind of concept is execution trace. So if we take the state of the computation every step of the execution, we get the execution trace. And this is nothing more than kind of a two-dimensional array. You can think about it where a column is a register and a row is a state of those registers at a given point in time. The next concept, and probably one of the more important ones, is the transition function. And a transition function describes how you get from one state to another. Basically, you take first state, apply some arithmetic operations to it, and you get a second state, and so forth. And the transition function, in this case, like it can take, the way I've described it here, it can take a vector of values and it produces the same, a different vector of values. It doesn't work on a single value. Then the next thing is transition constraints, and this is kind of slightly different from a transition function. Now we take two consecutive states and we run those through another function. And if we get a 0, that means constraints are satisfied. So the function g, in this case, it also works with two vectors. If we get a vector of 0s at the end, that means the constraints are satisfied. And basically, the transition constraints, they describe an algebraic relation between two consecutive states. And then the last thing is boundary constraints. And they just allow you to say that at a given point in time, or at a given step, a given register has specified value. Now, both transition constraints and boundary constraints, they actually kind of just different way to think about rational constraints. And, they kind of have at the most kind of basic level, they have the same representation. But conceptually, I think it makes sense to separate them. And I'll focus much more on the transition constraints in this presentation. All right. Any questions?
I have a quick question regarding the transition function and transition constraint.
Yep.
So constraints, does that mean that like the important thing from the point of view of the validity of the Stark is that the constraints be held? But is the implication then that the transition function is not necessarily a function, as in it can be like non-deterministic and it's possibly multiple allowable state transitions?
Yeah, you could do a lot. Like you don't have to, in theory, you don't even have to have a transition function. It's easier, at least for me, to think about that there is a transition function. You can generate the execution trace in whichever way, but as long as you can apply transition constraints to the execution trace, that's all that's needed. But from a standpoint of how you describe a computation, it might be easier frequently to have a transition function. So what you're saying is totally valid.
Okay, thanks.
Yep. So execution trace, and I described it in a little bit. It's a sequence of kind of states of the computation at a given point in time. And this is what I call a dynamic registers. There is another part to it, which I call static registers. And these are registers that can be generated without a transition function. These are registers that can be described very succinctly, both for the prover and the verifier. And the important part that the verifier can evaluate, can get the value of those registers at any point in the computation very succinctly. And just to give an example, one of such static registers could be a cyclic register, where you have a sequence of values that gets repeated over and over in the execution trace. This is extremely easy to describe, and the verifier just needs to know the description of those values that need to be repeated, and they can compute the the state of the register at any step. The other one could be what I call holy registers, where you have values spread kind of across the entire register. You don't really necessarily care about what the in-between values are, but you care that, let's say, at point, at step 1 you have 1, at step 5 you have 4, at step 4 you have 2, and so forth. And those are the two types that I kind of, at least in AirScript, work with, but it actually is pretty powerful. You can combine them in many different ways to get different shapes of the registers that can be communicated to the verifier in a very succinct manner and can be evaluated by the verifier in a very succinct manner. And AirScript actually uses this. If once we go through the examples, I'll show you how they're used to kind of read inputs and multiple inputs and ingest them into the computation state or execution trace. And just some general considerations about the execution trace. The length must be a power of 2. This is needed for efficient evaluation or interpolation and evaluation using FFTs. You can make kind of by default, all the dynamic registers are private, so the verifier doesn't know, cannot get the state of the dynamic register. But static registers you can make either public or private. If they're described, even if they're described succinctly, you can still keep the actual register private and only disclose part, a given point in that register using boundary constraints. And the field in which you're working should have a higher order roots of unity. And again, this is needed for efficient evaluation and interpolation using FFT. So now that I have a
question on the previous slide.
Yep.
Would it be fair to say that these static registers are kind of somewhat reminiscent of pre-processing in the case for?
I think you could say that. I mean, it's just really it's just a kind of an equation that gives you like a very succinct equation that a verifier can evaluate. So maybe there is some connection to that.
Yeah, I mean, verifier has, and it's kind of succinct.
Yep.
And it helps along with the computation.
Yep, exactly. I think it is similar.
And I guess my second question is, in practice, if you're interested in running your state transition function some number of times other than the power of 2, how do you deal with that?
So you can run it for X whatever steps you need, and then you can kind of zero out the rest. And I'll show you kind of a technique on the next slide, how you can have 2 different transition functions that do different things.
Okay.
So you can say like for the first, let's say you have 16 steps. For the first 10 steps, I do something, and then for the other 6 steps, I apply a different transition function.
Cool.
Okay, so a transition function, kind of just to extend the definition that I gave on the first slide, now that we know about static registers, is kind of very similar. It takes the current state of the computation. Now it also takes both static and dynamic registers, and it produces the next state of the computation. And the technique that I was talking about is, I don't know, maybe there's a different name for it, but I called it arithmetic switching. But basically what you can do is you can have 2 different functions. And you can have, let's say, a static register that takes some value at one point, and then takes another value at one point, and it could be like 1s or 0s. Then you kind of can turn on and off different functions. So in this case, when K0 static register is 1, F1 function gets executed, and when it is 0, the function 2 gets executed. And this is pretty powerful. You can extend this to a lot of different kind of complex scenarios where you have multiple transition functions. One could be calculating a let's say hash, and the other one could be doing something else. So it's pretty powerful. The one thing to keep in mind is obviously this, the more of this you have, the more it increases the computational complexity, because all of this are evaluated in parallel. So the more you add, the more you have to evaluate. And also, and I'll talk about this a little bit later, or maybe even here, it actually increases the degree. Like every multiplication you do increases the degree of transition function and constraints as well. And you need to get as much out of kind of in terms of the prover time, you need to decrease the, keep the degree as low as possible. So some considerations for transition function, you can do any kinds of arithmetic operations, multiplication, addition, division, and so forth. A degree of the transition function grows when a register is raised to a power, or you multiply 2 registers. And kind of one thing I didn't really talk about is this transition function only works with 2 consecutive states. But in theory, and not only in theory, but actually, there might be useful situations where you want to have what is called like a long-range transition function, where it can work on multiple states, not just the 2 consecutive. Like basically, it takes more than 1 state to produce the next state. An example of this could be like a Fibonacci sequence, where you actually have to rely on the 2 prior states. There is a way to represent Fibonacci sequence using this type of a function as well, but a more natural way would be to be able to rely on the 2 previous states. I'm not going to talk a lot about kind of long-range transition functions constraints in this presentation, but there is a different way to describe a transition function in a more powerful way, but it also adds much more complexity. All right. And transition constraints, now just to update the definition that I gave on the first slide. Again, now it takes the first two states of the computation, and it produces, as well as the static registers, and it produces some sequence of values that now become your constraints, that if they evaluate to 0 for those steps of computation, then your constraint is valid. And frequently, if you have a transition function, and this is where sometimes it's useful to describe because you kind of kill two birds with one stone, is that if you already have a transition function, frequently your transition constraint is just you take kind of a state of the computation, apply a transition function to it, and subtract that from the next state, and that should give you 0. But it's not always like that. Sometimes you can have split your transition function into two different functions and apply, let's say, the first one to kind of the next step of the computation, the first one to the previous step, and subtract one from the other to kind of get evaluation. This is, for example, like, what the rescue hash function is doing. They have transition constraints that are not kind of just as simple as subtracting the result of a transition function from the next state. Some consideration, division, at least within AirScript and kind of at least conceptually, I'm not sure how to do division within the transition function, but you can emulate it using kind of other means. The degree of the transition function, this is transition constraints. The degree of transition constraints do not have to be the same as the degree of transition function. So to bring up the example of rescue again, the transition function has extremely high degree because they're raising registers to a very high power. But because they're splitting the constraints into two separate functions, and they're able kind of to do the inverse of the original kind of raising to a power, the degree of the constraints is much, much smaller. It's actually like only 3, where the degree of the transition function is actually close to the magnitude of the modulus of the field. So you can, and again, as Justin said before, the transition constraints are the ones that you really care about. The degree of the transition function doesn't really matter that much. The degree of the transition constraints matters a lot. And again, this doesn't address the long-range constraints where you can actually work over more than just 2 consecutive states. Okay.
The emulation of the division is just multiplication with a helper.
Yep, exactly.
One more question.
Yep.
What is the most general form of transition constraint function? You show 2 variants, and is the second is the most general or not?
I mean, you can make it almost anything you like. In the simple computations, like most frequently is the frequent one, at least the ones that I've been working with. I think as your computations get more complex, you will need to apply slightly more complicated transition constraints. So I'm not sure if I've seen enough to say what's the kind of the more general case. The things that I've been working with more frequently is just the simple constraints.
Okay.
All right. So the next thing is just kind of very, very basic overview of kind of how Starks work, and this should be somewhat redundant to what I've already said. But basically, you start with some set of inputs. You run a transition function, and you generate an execution trace, and then you apply your constraints to the execution trace, and you get the constraint evaluations. And then these get kind of using linear combination of random linear combination that they get compressed into a single composition polynomial. And then you use the Fry protocol to kind of build a Stark proof. And I've skipped a bunch of things here. There is like a degree extension and a bunch of other things that happen here. But at the high level, this is kind of the process. And the important thing is really that the first 2 steps are computation specific, and the other 2 are computation agnostic, meaning like once I have my constraint evaluations, I don't really, there isn't really anything different that I would do for one computation versus another computation. And the way I think about them, or at least in the libraries that I work with, the way I split it up is that AirScript is kind of used to handle the first two steps. This is what kind of you use to describe the computation, as well as what you use to generate execution trace and the constraint evaluations. And then GenStark is a library that picks up what AirScript generates and kind of applies the other stuff to generate the Stark proof. And kind of on the high level, the major components of AirScript is that it needs to have these three things. It needs to have the logic for how you generate execution trace. It needs to have logic for how you generate constraint evaluations, and also include some logic about how you interpret the inputs that you pass into the script. And the way it works from kind of a toolchain perspective is that you have AirScript source. It gets compiled into AirAssembly module. I think I mentioned it, but AirAssembly is kind of a low-level representation. It's not something that you would use to like write, but it is much easier to work with this very low-level representation. And one of the things that I'm working on is trying to make it composable, and it turns out that making things composable at the lower level is much easier than it is at the higher level. So I've created AirAssembly so that I can make AirScript composable. And then GenStark, proof verifier kind of evaluates the module, builds the proof out of it, and you can also use it to verify the proofs as well. And I'm hoping that AirAssembly can be kind of generic enough where other people can create different types of scripts. So AirScript is just one example, but maybe somebody will come up with something else that compiles to AirAssembly. And then maybe in the future as well, we'll have different provers as well that can work off AirAssembly. You'll have something written in WebAssembly or something written in Rust and so forth. But as of right now, I think GenStark is the only prover verifier that works with AirAssembly, and AirScript is, I think, is the only language that compiles into AirAssembly. I mean, I just finished AirAssembly like a month ago, so I wouldn't expect anybody to do anything. All right, any questions before we jump into an example?
A quick question I have is this like a passion project for you, or are you funded by an entity?
I mean, it started out as a passion project, but actually Ethereum Foundation gave me a small grant, so I'm kind of working on with the help of Ethereum Foundation.
Excellent. Awesome, Ethereum.
All right, so let's do, so I have two examples prepared. The first one is AirScript for MiMC calculation, which is very simple. I think most of you are probably familiar with what it is. And then we can go into something more complex, which is a Poseidon hash function. And I think we should have enough time to cover both. But we'll spend probably a bit more time with MiMC just to get the concepts down. Okay, so this is, kind of MiMC calculation. You take the current state, raise it to the power of 3, and you add a round constant to it. And this is the current state, this is the round constant, and this is how you get the next state. And this really translates to just having one dynamic register and having one static register. For our example, we're going to use a few parameters. So we're going to say that our input value, so you need to start somewhere. You need to start cubing something. So the input that we're going to start with is going to be 3. We're going to use a very simple cycle for round constants, is just repeating 1, 2, 3, 4. And we're going to have a very short computation. It's going to be 64 steps. And then we're going to use a very small field. It's going to be a 32-bit field. For Starks, actually, the size of the field doesn't matter that much. You can have a 32-bit field. You can have a 256-bit field. There are some limitations, like if you use a 32-bit field, I think doing anything that has to do with elliptic curves becomes very, very difficult. But from a security standpoint, you can have, if you don't really need to do anything with elliptic curves, you can use a 32-bit field, for example, and still kind of get away with it. Okay, so if we run this computation using these parameters, we will generate kind of like execution trace like that looks like this. So you can see the sequence of 4 values repeating here, and you can see we start out with 3. We cube it, add this value, so it's actually works like this, and it works like that. So it's fairly straightforward. So let's do this using AirScript, and I'll be sharing my screen here. But if you guys, so the project, the GitHub project that I kind of shared has basically this project, and I'm going to show how to use it. But if you want to kind of follow along and write it on your machine, you're more than welcome. First thing, let me see. Can everybody see the screen, or should I zoom in?
I can see it.
Okay.
Oh, also, I wanted to say something. If anyone has any questions while Bobbin is speaking, just stick them in the chat notes, because we'll like check those out in a bit. Forgot to mention that before.
All right. So the way you write AirScript is first you kind of define a Stark. So the way you do it is you type define and give it a name. And you would say, let's say, and we need to give the modulus to the field. So we're going to use this very simple modulus. So this is basically, we've created a Stark saying, our Stark is going to be in this field with this modulus. The next thing, let's define a constant. So we're going to be raising something to a power of 3. So we're going to have our, let's say, I'll call it alpha, and I'll say it's going to have, it's going to be 3. The next thing we need to define are the static, is the static register or our round constant. So let's say, so we just pass in the round constant or our, we need to actually do this. So basically we're defining how our static register is going to be kind of generated. The next thing we need to specify, so we have a single input, so we're going to say, and it's going to be a secret input. And we're going to call it start value. And it's going to be a field element, and it's going to be just one field element. So we don't have 2 registers or anything, so we only have one element that we need to pass in as a start value. And then we're going to define our transition function. That's kind of the next step. So we kind of set up all the kind of properties, basic properties, but now we're going to define a transition function. And we only have one register, so we just say transition 1 register. And the way we can kind of read the inputs, and this is a bit tricky, but for me, for a MiMC example, it's going to be simple, but we'll need to somehow specify, at which point to read the inputs. And the way you do it is in AirScript, there is a for each loop. And we would say for each start value, we'll do the, kind of this set of these steps. The first thing we'll need to do is initialize our execution trace. And this is kind of the first step of the execution that happens. And we would say, it just yields, actually, if I could spell right, start value. So the first step is going to just initialize itself to the start value that we've passed in as an input. And then we would say for steps from 1 to 63, so we're going to run for 63 steps, 64 including the first step 0 that we initialized to. We're just going to say our computation is going to be equal to the current state. And one thing, kind of every transition function and transition constraints has an implicitly 2 variables passed into it. It's the transition function actually has only 1 variable passed into it. It's the variable $R, which basically holds the current state of the computation. And there's also $N, which holds the next state of the computation, but it's only accessible in transition constraints. But here we would say we will take the current step, and we're going to raise it to our power of alpha, which is 3, and we're going to add our round constant to it. So this is the entire transition function. There isn't much more to do. And then we need to define our transition constraints as well. We have one constraint. And this constraint is going to basically say for all steps, because it's not really doing anything special. It's just taking the next step of the computation and subtracting from it the kind of transition function evaluated in the previous step. So we can just say for all steps do the same thing, and it's going to be enforce that transition of our current state is equal to our next state. And on the background, all it does is just says, run the transition function and then subtract the results from the next state. Now, I went through this fairly quickly. Does anybody have questions, or is there anything specific I could talk about to make it more clear? All right.
One question.
Yes.
Here there are nested loops. So why cycle over from 1 to 63 nested? And in GenStark, I have seen two-dimensional inputs arrays, not one-dimensional. So we could set a set of inputs for one start value element.
Yep. Yeah. So if I had two, for example, if for whatever reason my start value of 2 elements, I could have just said 2 here, and then my start value would result to a vector of 2 elements. And I should probably just mention this. So in AirScript, there are several types. So there is a field element type, and then there is a vector, and then there is a matrix. And the vector is just the way you would expect. It's kind of a sequence of values, an array of values. And the matrix is a 2-dimensional matrix. So your variables can be either single field elements or vectors or matrices. And you can do arithmetic operations with them kind of just as easily. So you can add 2 vectors together, and that would be element-wise addition. You can add 2 matrices together, and that would be kind of element-wise addition as well. You can multiply matrix with a vector, and that would be kind of matrix multiplication. And I'll kind of cover that in the example of Poseidon hash function. I think it would be, you actually work with vectors there, so it would be kind of a natural place to cover there. But yeah, so there are those 3 types, 3 basic types, and then the arithmetic operations are kind of just addition, subtraction, multiplication, division, and vector or matrix multiplication is a separate arithmetic operation.
Okay, is it just syntax sugars or not?
It's just syntactic sugar, so you can all express it as like, and that's how I actually started out when I tried to first write the air for, let's say, Poseidon or rescue hash function. I started out just having simple arithmetic expressions, but it just becomes too cumbersome when you need to do matrix multiplication, for example. Just describing that as individual statements becomes very cumbersome. So that's syntactic sugar that then just translates into, like individual.
Okay, thank you.
Yeah. All right. So this is our MiMC kind of error for MiMC, and just to show how this works, let me clear what I've done before. I can run this example, and let's say we want to start with value 3, right? So if we run this, I probably mistyped something somewhere. Let's see, or I should save it first. Let's try. So I either didn't close something or have an extra. Well, luckily I have an example saved that should work. Curious what I screwed up.
Maybe you didn't have the cycle keyword back then?
Maybe. Well, I made that mistake somewhere, but so this version works. Let me kind of do it again. So this is our execution trace, and we can see our dynamic register here. So AirScript on the background builds several static registers that control the flow of the execution to help kind of with the execution. This is our dynamic register that we defined explicitly, or sorry, static register, that is the cycle of 1, 2, 3, 4. But AirScript actually built 3 other static registers. The first one is where the inputs come through. So like you can see the value 3. It's rotated here, and there is a reason for that, but I'm not going to get into it right now. But basically, this is the register that kind of where the inputs would go in, and this register, another static register that gets generated, it just kind of a switch register that I kind of explained the arithmetic switching. So here it says, you know, at this point you need to read the inputs, and at this point you apply the transition function. And this is kind of the inverse of that register. It's you know, you can do it in theory only with this register, but this actually makes it simpler, fewer computations, because the trace for the static register is very easy to generate, but kind of complicating the transition function constraints with, you know, additions and subtractions sometimes may not be worth it. So in this case, I just generate another register. It's a little bit simpler that way. But here's our trace. I mean, if you go through this, you should get to this, and this is kind of my separate validation. I ran the MiMC function separately outside of Stark, just like a simple, you know, function written in JavaScript, and it should resolve to the same value. We see we get to the same value in both cases. We can actually run it for, let's say, multiple values. So let's say we run it for 3 and 4. So now our execution trace is double of that, because we do 64 steps for each input. And you can see, for example, that this register that kind of reads the inputs, you know, here at step 63, it was equal to 4. So like it gets to this value and then it resets and now runs with the value 4 as the transition function. So if we did it correctly, you know, the first one at step 63 was this, and then the other correct value then is going to be this. Any questions about this?
Why it would be better or worse to have one long column as opposed to 2 columns if you have 2 inputs?
It's easier to, I mean, you can have multiple inputs. So in this case, we have a single input. Let me see, where is it? So in this case, we defined a single input. If we had defined 2 inputs, we would have 2 columns for input. So each input gets a separate column, and you can actually provide, like in the way here that I've provided 3 or actually 2 values as an input here, you can, for each of the inputs, you can provide kind of, it's an array of values, so to say. So I'm not like, if you had different inputs, I don't think it makes sense to combine them into a single register, but if you have kind of the same input can take on many values, and that's why you need a single register to represent all of it. Does it make sense?
One more question.
Yep.
If we set 3 and 4, does it check at border step transition constraints or not?
It does not, but that would be handled by boundary constraints. So when you generate a proof, so this step just generates the execution trace. There is another step that could generate constraint evaluations based on this trace. And then the other part that is, I'm not kind of showing here, is that to generate a proof, you actually need to have boundary constraints, because just running this kind of having execution trace doesn't give you much. But what you would do is, once you have the execution trace, you would say a boundary constraint. Let's say a boundary constraint is that at step 63, the value of the register is equal to whatever this is, and at step 127, it is equal to this. And this way, you can convince somebody that you've ran the computation for 64 steps and you got this result.
Okay.
But that's done a bit separately. So like when you generate a proof, you would say, for this computation, my assertion in GenStark boundary constraints are called assertions. You would say the assertion is that the execution trace has this value at this point at this point in execution trees.
If I want to take this constraint system and deploy it on Ethereum, does your software generate a smart contract for me?
It does not yet generate a smart contract. I mean, it's not something I've been working on so far. I kind of mostly been working on the AirScript, but I think the smart contract would not necessarily be specific. Well, you could make it specific to a computation, but it would be more of a verifier. You need to have a verifier that would take the result of this, and then I don't think you would want to generate execution trace on the as a part of the Ethereum smart contract. You would want to verify that somebody generated the proof. So I think it's a bit different. There is probably a way to think about how you can create a smart contract out of it, but I haven't gone this far yet.
And if we were to go down this route, would it be a different smart contract per constraint system?
Yeah. So if you so let's say a verifier, right? So every time you define a computation, it has some specific parts to it. So the contract would be different for like, you know, MiMC versus the rescue versus like a Merkle branch proof or whatever. They would have different arithmetizations. So an arithmetization would require a different smart contract. So you would not be able to have a generic, I mean, maybe, no, I don't think you would be able to have a generic, and maybe I might be wrong on that, but that's kind of my thought.
You'd have to on-chain describe the different rational constraints you use and how they apply. Like you'd have to sort of serialize that as part of your problem description, which is like, which would probably be very expensive.
Yeah, there is like one of the things that I've been thinking about, and is like you can create a Stark that can you know, interpret a given like very simple language, for example. So you can have a smart contract that has a single Stark, which you can feed kind of like let's say some language that does additions, multiplication, and so forth, but it would be slightly different from this. This kind of describes the execution tree, like the computation itself, and there you would have a computation that can verify other computations. So there are some interesting ways to think about it, but I don't think you would necessarily kind of be able to build a generic Stark verifier in Ethereum, at least at this point.
Were you talking about things like IVC, incrementally verifiable computation? I think there is a paper on this, but no implementation because it wasn't efficient enough. I can try to pull it up if it's interesting.
So Michael from StarkWare sent me a private note. I think it's quite interesting. So he basically told me that, you know, the question versus doing a single long column versus two shorter columns. Mm-hmm. Well, if you use two columns, the verification is a bit more expensive, but I guess the proving time is less expensive, and vice versa. If you have a single column, then the proving time is more expensive, but the verification is a bit cheaper.
Yeah, I think that's fair. I think the question is like how many inputs do you have versus you know, at least the computations that I've been working on with so far, they don't have a lot of inputs, and usually those inputs are, you know, maybe like limited to, you know, like let's say half a dozen to a dozen of different inputs, and each input again can be like an array of values or nested array of values. So maybe if you have a lot of inputs, it might make sense to optimize it even further for the verifier. But I think at least with like a small number of inputs, the verifier, like there's almost no difference.
It also has a complex difference on proof size, like whether you use one or two registers. So if you use two registers, your degree halves, and then you have potentially one less round of Fry, which could save proof size. But you've also added one more oracle, which could then increase proof size. So like.
So actually, that's a very valid point. And another thing I want to say about the input registers is that kind of each register that you have, and that applies to dynamic registers and secret static registers, they increase your proof size. So like if you're working in, let's say, 256-bit field, every register increases your proof size by probably like between 1 and 2 kilobytes. So if you have just one register, you know, and you add another, you increase the size. Like, I mean, there are other parts of the proof that are bigger than that, but if you have too many registers, your just number of registers would dominate your proof size. All right, should
So
we do?
Each static register increases proof size by 1 or 2 kilobytes?
It's each dynamic register and each secret static register. So a public static register does not affect the proof size because it's communicated to the verifier kind of separately. It's not part of the kind of the proof that gets sent. It's part of the description of the computation itself. But if you have a secret static register that gets encoded into the execution trace and it kind of becomes the part of the proof, then it increases the proof size by between 1 and 2 kilobytes. And that's only in 256-bit fields. If your field is smaller, the impact of an additional register is much smaller as well.
But what if your secret register is like succinctly representable?
Well, in that case, you need to somehow communicate that succinct representation to the verifier, and then it becomes not secret.
Okay, I see. So that's only for applications where you care about privacy.
Yeah. Okay. Let me show you how we're doing this time. So we have 9 minutes. Let me try to run through the example of Poseidon hash function in that time. So same thing. Let me just copy it so that I don't waste time typing it up. But so here is the Poseidon hash function. This is air for the Poseidon hash function. We use the same field. Now we define we have an MDS matrix as part of the hash function, and it's this is very simple. I'm using a small field, and I'm using only 3 registers. Actually, 3 registers should be enough, even for in a large field for like a real hash function. So here we have the 3x3 MDS matrix that we define. We have our round constants, and there are kind of 3 registers. So our round constants, instead of being a single element, is now 3 elements. And instead of like typing up the values by hand, you can have them here by hand as well, like specific values of the round constant. But here in AirScript, I have ability to just pseudo-randomly generate them from a given seed. So here it's just pseudo-randomly generate them from like different seeds, and there's going to be the number of constants generated. So you can think about this just as an array. Each of this is an array of 64 values in the field pseudo-randomly generated. Now, as a hash function, this is a hash function that will take 2 values and hash them together and produce the output as 1 value. And what we do here is that we have 2 inputs, and each of them is a single field element. And then for each combination of these 2 inputs in a transition function, the first row will be just these 2 values, and we put 0 as a 3rd register. So the way Poseidon hash function works is that you can have 2 registers. It will, I think the first 2 registers are the rate, and the other one is you can use it as a capacity, so that it's kind of used in the hashing process. And then the Poseidon hash function has different functions applied depending on which step you're in. So in this case, this illustrates how you can use 2 different transition functions. So this is a transition function for the full round, while this is a transition function for the partial round of the hash function. And constraints are very simple. They're just again, for every step you just apply transition function to the current state, and then you subtract it from the next state. I know I went super quickly, but anything that is specifically confusing here? One thing I should mention is that this sign is actually a matrix multiplication. So what we do here is that we take our vector of 3 registers, we add our vector of round constants to it, so it's like element-wise vector addition. We raise the resulting vector to the power of 5, which means we just raise every element of the vector to the power of 5. And then we kind of do a multiplication for matrix and vector multiplication, and that's the output of our kind of computation. Does that make sense? Or if it doesn't, speak up.
Is PRNG defined somewhere else, or?
PRNG is kind of, you can think about as a built-in function that I've described it in definition of air assembly actually, but it basically appends. There is a way how it generates values. It applies SHA-256 function to a given C, then it kind of appends the, I don't remember the exact definition that I used, but there is a description of it. If you're interested, I'll send it to you.
In the last loop, like enforce 3 constraints, what is $n?
$n is the vector that contains the next state of the computation.
Okay, it's just a macro for any constraint?
Well, so there are, the constraints definition has 2 implied variables, and this $r and $n. And $r contains the current step. It's basically a vector. So like if I go back to my presentation, when I described the state of the computation, right? So you could have like 3 registers in this case. And in this case, your $r will contain the values of those 3 registers at the current step, and $n will contain the value of those registers in the next step.
Okay, that makes sense. Thanks.
Mm-hmm. All right. So
can you not support more than just the previous step?
Yes, you can, and AirAssembly actually supports this, but for simplicity, AirScript doesn't yet, because if you support more than it's possible to do that. It adds a bit more complexity, and I just haven't spent time on building in that complexity.
Cool.
Also, this seems like really tailored to some cyclical computations. If I actually have to specify what I want to do at each step, then do I have to like write this construction every time, like for step 1, for step 2, or for step 3?
Yes, if you have like computation changing from one step, like if you apply a different transition function every step, then it will be very difficult to describe this using AIR constraints, because AIR are specifically tailored to describing cyclical computations that happen over and over again.
Sure, makes sense.
Yeah. So, but let's run this example. So, and let's hash 2 values. Let's say 42 and 43. So here's the execution trace. We have our dynamic registers. They get initialized to 42 and 43. This is the capacity register that gets initialized to 0. And then it applies those transition functions. You can see this is, let's see. So this would be our, these 3 registers are our round constants generated pseudo-randomly. And these registers actually control the switching between different so like you can see that for the first 4 steps we will apply one transition function. Then for the next 50 or something steps we apply the other transition function. Then again we apply the first. So this basically register is representation of this structure, where we say for the first 4 steps, and then for steps 60 to 63 we apply this function, and then for other steps we apply this function. So this is kind of, where did it go? This is kind of the switching register that controls the execution of different hash functions. And then you have your input registers here, like 42 and 43. And if you run the hash function, here's my control value. Your result should be in this register, so they align and basically generates the correct value at the end of the execution trace.
Bobbin, are you taking an eye on the chat? Because there's a few questions in there. I just want to make sure.
I was not actually. Let me see if I can.
Maybe they are, but.
Sorry about that. Let me see, I actually need to find where the chat is.
Well, one was from Dev. I don't know, Dev, did you say that out loud, actually, that one?
I was saying something about IVC, and I was just saying in chat I misremembered that result.
Okay. And then Igor, you posted something as well.
Yeah, what do you mean by non-deterministic or indeterministic examples?
For example, if we need to check that the number is 0 or not 0, and put the result to next registry.
I don't have those constructs yet. I have some ideas of how to build them. I don't think they're conceptually very difficult to do, but I haven't done that yet. I think kind of my next to-do thing in terms of AirScript is to build a composable AirScript where you can import. So let me actually show a slightly more complicated example. I'm not going to go into details, but this is how you do a Merkle path verification using AirScript. And let me just copy it so I don't have to type it up. So this is, for example, a way to do a Merkle path verification in AirScript, and you pass the leaf register, you pass now you pass like a multi-dimensional set of values as one of your registers. Actually, it's two of your registers. The index bit is also kind of binary expansion of the index value. And here you just run a Poseidon hash function, and it creates a lot of like unneeded things, because I don't really need to know the hash function that I want to run to do a Merkle branch verification. So ideally that should be written somewhere else. So like my next step that I'm working on is being able to say like import Poseidon hash function, and then instead of writing this here, you could just say, run Poseidon hash function for this number of steps.
Okay, it is interesting, but Merkle proof computation is deterministic thing. In deterministic examples is bitification, for example, if we need to split one field element to set of bits, so such things.
I mean, right now you would do that kind of a priori by yourself. So you would like create like in case of this example, for example, one of the inputs is expected to be a binary expansion of a index of the leaf that we're trying to verify the proof for. So it's not built into the language, but you can create an input that you kind of like, when you submit it to generate a proof, you already kind of did the binary expansion. I think it would be useful to have more complicated constructs here in AirScript that would do it for you. I just haven't gotten to them yet.
Okay, and such constructions couldn't be written in AirScripts. It could be added into AirScript as primitives only, yes?
Yeah, they're not here as primitives, but you can emulate them. It's slightly more difficult, and you have to do a lot of, maybe some bookkeeping by yourself, but I think you can emulate most of the things. That it's just not going to be easy to do it.
Okay.
And if you guys are interested, I can just run this example of Merkle proof as well. So just to show you a slightly more complicated, it's going to be more registers. So here I want to generate a distribution trace for verifying that at index 3, the value of leaf is 4, and this is my Merkle branch path. So here is my execution trace. You can see, for example, these are the input registers, and I'm reading in the values of the nodes in the kind of Merkle branch, and kind of this runs the hash function. I mean, it's slightly more complex. I don't have enough time to explain, but it like this uses you can see like it hashes, the leaf in the branch from the, or a leaf and a node from the branch, or its opposite, and then every 64 steps it figures out which one of these two is the correct one, and then it continues to the next step. And all of this is in the repo, so if you guys want to play around with it, if you have any questions, just ask. You can play around with these examples very easily.
Cool. Are there any other questions? I guess if not, then I think that could round out the study club. So awesome. Thank you again. Thanks, Bobbin, for putting this together.
Yeah, thank you guys.